Graphs of basic polar equations. I will show you a few graphs of equations in the polar coordinate system, only a few. Okay, we will not dwell into this so much because what we are after is integration. What we are after here is to show how we can apply integration, okay, to get the area of regions in the polar coordinate system. That is what we are after. We will see circles in the polar coordinate system, but the equation that will define those circles are different from how we shall define it in the rectangular coordinate system. So this one, for example, letter A, is a set of points. That is a set of points whose distance from the pole is equal to A. So that is a circle. So for example, this one, R is equal to 2. That is a set of points in the polar coordinate system whose distance from the pole is equal to 2. How about this one? So this is R is equal to 2 times sine of theta. We are in the polar coordinate system. If we are in the rectangular coordinate system, the sine function ought to give you your sine waves, but not here, not in the polar coordinate system. Now you may be wondering why this becomes the graph of this equation. R is equal to 2 times sine of theta. Well, this is what you can do, okay? You can produce a table of values, okay? Table of values. This is your theta, and this is your R. When theta is equal to 0, sine of 0 is 0. 2 times 0 is 0. And so, the point here in our polar coordinate system is going to be this, 0, 0. Okay? And that is that point. Okay? And then, you will rotate your angle. So you begin from the polar axis, and then you will rotate this, okay? And as this ray rotates, it will trace a point or a set of points along this circle. And those points, the distance of those points is defined by this. R is equal to 2 times sine of theta. Okay, so let's say, for example, our angle now is pi over 2. So what is sine of pi over 2? It's 1. And 2 times 1 is 2. And so that's why we have that point. Okay? We have that point. And then you go on, you continue tracing your angle from pi over 2 to pi. Okay, so what is sine of pi? Sine of pi is 0. And 2 times 0 is 0 again. And you return to this point. After sweeping an angle that is equal to pi radians, the value of R is equal to 0. So you return to where you began. Well, this one will be a variation of your equation when A is equal to -1, for example, okay? So R is equal to -2 times sine theta. This one is how your graph will appear when your equation appears this way. R is equal to 2 times A times cosine of theta. Okay, so let us try it. Let us see. Let us verify this circle. When theta is equal to 0, R is equal to 2 times cosine of 0. Cosine of 0 is 1. So R is equal to 2. Okay? And that is that point. When your angle is 0, R is 2. And then this is what you do. You will trace an angle from 0 to pi over 2. What is R? Well, cosine of pi over 2 is 0. So R is 2 times 0, which is also 0. And that is your point. Okay? Now, you can generate this set of points below the polar axis by rotating your angle clockwise. Okay? So you can begin from 0, and then you go clockwise. You go to negative pi over 2. Okay, so this is negative pi over 2. And you will generate these points. Okay, r is equal to 2 times cosine theta. So this is the case when a is negative. Okay, cardioid. Okay, so the name itself is telling you something. The graph ought to look like a heart. And this is the equation. R is equal to a plus or minus a sine theta. And the other one is R is equal to a plus or minus a times cosine of theta. This one is the case for r is equal to 2 plus 2 sine of theta. So a here is equal to 2. And the axis of symmetry being spoken about here is pi over 2. So this is your pi over 2. So this line sweeps an angle that is equal to pi over 2. Okay, again, let us verify this. When theta is 0, sine of 0 is 0, so r is equal to 2. And that is that point. And then you will trace an angle. As you trace an angle from 0 to 2 pi, okay, it will produce a series of points whose distance from the pole is r. So let's say, for example, our angle is pi over 2. Sine of pi over 2 is 1. 2 times 1 is 2. Plus 2 is equal to 4. And that will bring us to that point. Okay? When theta is equal to pi, okay, let's say, for example, this is pi. Coming from pi over 2, you are now going to pi. Sine of pi is 0. 2 times 0 is 0. 2 plus 0 is 2. And so that is your point. Now, when you trace an angle, if you continue tracing an angle up to 3 pi over 2, sine of 3 pi over 2 is negative 1. 2 times negative 1 is negative 2. 2 plus negative 2 is 0. And so that will bring you to that point. Okay? And then continuing your revolution, going to 2 pi, this will bring you to that point. So this one is for r is equal to 2 minus 2 sine theta. This one is for cosine, 1 plus 1 cosine theta. And this is for 1 minus 1 cosine theta. Limacon and Lemniscate. Limacon. You know what? This one, I just copied this from the first book that I did for integral calculus. That was something like 6 or 7 years ago. And I used a different software for this one to generate the graph. Now I'm using GeoGebra and I am not yet competent. Okay, I am fumbling with the commands. I am lost often, which is why I had to go back to my old book. So this one is what we call Limacon. So they appear like the petals of a flower. And this one would be the Lemniscate. So this is how you present your equation for Lemniscate. Now, just like what I told you, we will not dwell so much on the graphs of equations that are defined in the polar coordinate system. Because I think that is a concern for analytic geometry. Although analytic geometry is developed under the rectangular coordinate system, I think it is just fitting to include there the polar coordinate system and the curves that arise from equations in the polar coordinate system. So I will stop here, okay? I will stop here because our concern really is how to use integration in getting the areas of regions that are bounded by curves in the polar coordinate system. I will stop here.